Okay, I posted Wednesdays over the weekend. I posted Wednesday's written work, 4 problems. So make sure you're showing all your work. When it asks for explanations, you're writing out full, complete sentences. This is the reason for this, is that you have to have some kind of practice writing out coherent, precise explanations, okay? So, as always, you'll be graded on completeness, showing all your work, and your ability to communicate what's going on. That's the point of the written work. Okay? We'll also have web work. I'll add that right after class. I'll put on the next web work. So look for that. Okay? Any questions about anything? Okay, so here's just a little warm-up exercise. Suppose a population of a colony, P of x, grows 21% every week. X is the number of weeks after the initial observation. Okay? So if we have 21%, is this consistent percent change? So what kind of growth is that? If you consistent percent change, that's exponential growth, right? We said exponential growth, we can kind of look at it in 2 lenses. There's this repeated multiplication by the growth factor on output to get the next output. And then also, that results in a consistent percent change, right? Both of those are true about exponential growth. Okay? So if you know the population 7 weeks after the initial observation, how can you represent the size of the colony 9 weeks after the initial observation? So this is both a task where you have to understand function notation, using this function notation, and also how exponential growth works. So see if you can come up with, and this is, you're not going to find, to do this, the restriction is you're not allowed to try to figure out what this px function is. That's going to be for a lot of you, that's going to be your inclination on how to solve these problems. You're going to try to take the initial information and put together a function, right? A, b to the x, right? That's our form for exponential growth, right? A, b to the x. That's what we've been working on. And so you need to be more adept than just knowing how to find that function and then use it, plug in, and do stuff with it. You got to know more than that. You got to understand more than that. So here's an example of this type of problem where you've got to be better than just knowing how to create the function and use it. Okay? So without creating the function, can you write an expression for what the P of 9 would be, the population after 9 weeks, given this information? Okay? So you know the population after 7 weeks. It's growing 21% every week. How can you write P of 9? Think about it. See what you come up with. Go. We're going to walk around. Everybody do it. Who knows what's going on? Who knows function notation? Who knows exponential growth? Show me. Show me. Okay. That's right. Use that to get population 2 weeks later. Okay, some people are getting it. It's an expression. You're not going to be able to figure it out because you don't know. So it's only going to be an expression. So it's not a matter of punching and calculating. Show me.
So the two.
Okay, you guys are good. That's good.
You're
Oh, you're trying to use it. You're trying to use the function. So you start with that. 7 weeks. For those who are trying to use population at 0, they're just go right for the population in 7 weeks. You got it. No. 7's wrong there. That's better. So you've got, how can you represent the population at 7 weeks? Can you write that? P of 7. P of 7. So now how, if it's growing 21% every week and you know P of 7, good? How can you get it 2 weeks later? Understanding how exponential growth works. Okay, we know the population after 7 weeks. How can we represent it? So we know it, but we don't. I didn't give you the number, but so we're supposing that we know that number. But so how do we represent it? P of 7, right? Okay, so that's not a true statement yet. So if we're growing 21% every week, what does that mean? What does that mean? Eric? Right, to get the next week, right? So if it's growing 21% every week, then we know that associated growth factor is 1.21, right? 1.21. So what happens to the population of this colony? Every week, if it goes up 21%, it's like multiplying that population by 1.21 to get the next population. So we want to get it how far in advance? 2 weeks. So we multiply it by 1.21. Is that it? What would that give me? It's what I've written in blue there. What would that give? P of 8. It'd be the next week. Well, we want it another week. So we got to multiply it by again. Okay, so you could write it as 1.21 squared. Okay, so so let's figure out what 1.21 squared is. Okay, so I'm going to come over here and say equals 1.21 squared. And I get 1.4641. So another way to write this is P of 7 times 1.46, so let's just say 1464. So what's the effect of multiplying by 1.464? That gives you the population 2 weeks later, right? So look, this is kind of the same principle. We've been working on what we call, this is like the 1 week growth factor. Every time you multiply by 1.21, you get the new output 1 week later. Well, what if you kept multiplying by 1.464? It would jump you 2 weeks, right? So you get the new output every 2 weeks later. Okay, so this is a growth factor too. This is also a growth factor. It's not what we've been calling the growth factor. The growth factor now we're going to call the 1 unit. Okay, the 1 unit growth factor. Because now we see that you can have other growth factors, so we need to specify. So before we just called that the growth factor. It was the multiplier on output to get us the next output. But really, there's more growth factors. This then is two-unit growth factor. So 1.464, it's a multiplier on what to give you what? Tell the person next to you. 1.464, it's a multiplier that multiplies on what kind of thing to get you what? Go, have a conversation. Okay, this Tyler. What did you say? 1.464 is a multiplier on what to give you what? Okay, yeah, to get he said on the output to give you an output like 2 ahead. So what is the 2 referring to? Input or output? The 2. That 2, the 2 units. Is it referring to output or input? Yeah. He says input. Yes, it's how far we're going to advance in input when we multiply 1.464 to get the new output, right? So we're going to get a new output 2 units of input later. So now when we specify these growth factors, we're referring to how many units of input we're advancing in order to get the next output that many inputs later. Does that make sense? So now by 1 unit growth factor, we're meaning, okay, this is just if you go 1 by 1 by 1 of the input. And you're going to multiply to get the next output. By next, we mean 1 unit advance of input. Now our advances of input are going by 2s, right? Because where's the 2 come in here? Right here. From 7 to 9, that's input. You see? That's input. But the result of multiplying by the growth factor is always output. You start with an output, you multiply by growth factor, and you get a new output. This is telling us the corresponding change of input for that new output. 7 to 9 is 2 units of input. Okay, so just a reminder, what is a growth factor? This is the centerpiece of exponential growth. It's a multiplier on any output that gives the next output. So now we need to specify, what do we mean by the next output? Do we mean 1 unit later? Do we mean 2 units later? Do we mean 5 units later? Okay, so now next is kind of a varying situation, okay? So here's a new situation. All right, so anyway, so it says an airborne disease starts to spread such that the number of reported cases grows exponentially. That's the setup. So the number of reported cases is growing exponentially. So here's the information we have. 3 days after outbreak, there's 174 cases. 4 days after the outbreak, 186 cases. So I have some questions for you here. Maybe? Okay, so before you find the 3-day growth factor, what are you going to find first? So maybe there's a question 0 here. So we'll start with the one-day growth factor, what we've been used to, okay? So given the information that you have, can you find the one-day growth factor? And then from that, can you find the 3-day growth factor? And then can you write the function for the number of reported cases after X days? So you've got some work to do here. I'm going to take roll. Jerome can help you. You can work together. But you got some work to do. Some of it's going to require some thinking. And we'll revisit in a second. Is that a question? Okay, Cody. How do we do on the one-day growth factor? How did you figure that out?
I divided 186 by 174.
Okay, because, right? Because?
That gives us the growth factor from 174 to 186.
Right, we're asking what number do we need to multiply 174 by to get 186? How would you find that? What he said, you would divide 186 by 174. Right? 174 times that ratio would give you 186. And what is that? Cody, go ahead.
1.068.
How do you do? Agree? Okay, so this is our multiplier. And if it's exponential growth, how would you find the number of reported cases on the 5th day? If it's exponential growth, how could you find the number of reported cases on the 5th day? Ashley? It's true exponential growth.
So you take 186
Take-
times 1.06.
She said 186 times the 1.068. That's how it works, because to get the next output, in this case, 1 day later, you multiply by the one-day growth factor. So if we know what it is at 4, we'll multiply by 1.068. It'll give us how many cases at day 5. Okay, so now what about the 3-day growth factor? 3-day. Is there a question?
Yeah, that's a good question.
Yeah.
When we're regularly finding the growth factor,
Uh-huh.
decimal places is appropriate.
Enough. So it kind of depends on the situation, right? So if you're given the percent change, then you're going to have it exactly, right? So what was the next decimal place?
It was 9 or 8, so that's why.
6, 8. Oh, 6, 8 what?
9.
6, 8, 8.
Oh, 688. Yeah, so we're definitely want to do 1.069. Yeah.
So you want 3 places or? 'Cause I did 2. Because I only did 2.
Well, okay, so to say 1.07, that would not be enough. But 1.069, that seems it's reasonable. There's like no cut, there's no hard and fast rule. So when you're doing it on web work, so this becomes an issue on web work, you can enter things like this, right? If it asks for the growth factor, you could just enter that expression, then you never have to worry about how many decimal places, because that'll be exact.
That's so helpful.
Okay? So in web work, let it be your calculator so that you don't have to decide how many decimal places to put in your answer. You can just put expressions in there. And if you're not sure if they're complicated expressions, use the preview button, because the preview button will give you a nice image with fractions and everything, so you can make sure you're putting in what you intend to put in. Okay? So, so what is this? Now we're to the nearest percent, right? That's going to be 6.9% change. Seems reasonable, okay, for in this situation. Okay? We wouldn't want 7, probably isn't enough, but 3 more decimal places is too much. So something like 6.9, or maybe you could do one more. If you did 8.0688, that's about the right for this situation. That's about the right thing. Okay, so there's no real hard and fast rule. In order to get credit for web work, just put in expressions like this, but know that know how to get a good approximation. Okay, how about the 3-day growth factor? Let's see. Yeah, Danny.
You would put that percentage right there to the 3rd power.
Is it a percent? Is this a percentage?
I mean the rate of change.
Growth factor, right? So we know if we want the 3-day growth factor, it's like multiplying by this thing how many times? 3 times. That would get us 1 day later, this would get us 2 days later. If we wanted to know the output 3 days later, we would multiply by this whole thing, right? That would give us the output 3 days later. One growth factor for each day. And so then, that equals 0.069 to the third. And as an approximation, so if we're building approximations upon approximations, let's go ahead and be exact here. So what I'll do here is I'll go equals 186, right, divided by 174. So that's exact, and then we're going to do what to that? Cube it. Raise it to the third. So this will be exact, and then we can decide how we want to approximate it. So we could say 1.221 or 1.2215. Okay? That would be our 3 day. What was the next question we had? 3 day. So 3 day percent change. 3 day percent change then is? Yeah, so we know the 1 is what we keep, and so with growth, it's pretty easy to see on some of these what the percent change would be. So that would be 22.15%. If you had 22.1, that's okay. Every 3 days, the number of cases is growing 22.15%. So finding a percent change from these multi-unit growth factors is the same as the way you found it from the 1 unit growth factor. Okay, so in this case, you subtract 1 and multiply by 100. But you can see it right there. There's the 22.15% increase. Okay, so now if we want to write a function, we've got, for the number of reported cases after X days, we've got the 1 day growth factor. What are we missing? We need the initial value. We know our function form is ab to the x, right? ab to the x. So how are we going to find? There's different ways to do this. What's one way we need to figure out this initial number for x equals 0? Yeah, Nicholas. Okay, how many? So you're going to take 174 and divide it by 1.069. Will that, and that will give us what? That'll give us this one, right? Yep. And then? Okay. Good. So he's thinking if we go backwards, if we go backwards in input, then instead of multiplying by the growth factor, we would divide by the growth factor, right? So he just said take the 174. Keep dividing by 1.069, or this 186 over 174, until you got back to day 0. That's good. So how many times do we divide by this number, 186 over 74? 1, 2, 3. Yep, so we could do it down here. Equals, this is a valid way to do it. There are others. So 174, say divided by, oops. All right, 186. Divided by 174. No, I had it right before. 174 divided by this number, 186 divided by 174, and that 3 times. So let's put another set of parentheses just to make sure. Go away. There we go. So I took the 174, and instead of multiplying it by the growth factor, now I'm dividing it by the growth factor, and that 3 times to get me back to day 0. Do you see it? So it's looking like the initial number of cases was 142, right? Because it's not going to be a fraction of a person, so we kind of just round to the nearest. In this case, we'll round to the nearest whole person. So we're assuming here that the initial number of cases was 142. So therefore, the function is, where's this. So this is the function, is f of x is going to be 142. All right, and when you see that 1.069 to the x, you see 1.069 to the x, and you imagine what? You imagine, Matt says, 1.069 multiplied together x times. So if we're talking about day 10, x is 10, and we see 1.069 multiplied together 10 times. One time for every day that went by, since it was 142. The cases was 142. Okay? So again, exponential growth is about what operation? Is it about exponents? No, it's about multiplication. This is just an exponent, like we said last week. It's just a convenient way to express multiplication over and over again. That's what that's about. So the focus of exponential growth is not exponent, it's multiplication. An exponent is a convenient way to show multiplication. Okay, so now we want to write a new function g of n, where n is a number of 3-day periods. Okay, so g of n, initial value in this case? Same. And so now every time n advances by 1, 3 days will go by. So what will I put in here? I'm going to put the 3-day growth factor in because every time n increases by 1, I want to multiply by the 3-day growth factor. So I can put in my 1.22, just leave it at that. 1.221. That looks like a 4. Okay. So now we can write, now that we have multi-unit growth factors, we can write functions based on those multi-unit factors as long as the input is the number of, in this case, 3-day periods. So if n is the number of 3-day periods, then the growth factor is going to be the 3-day growth factor. Okay, questions on this example? All right, let's try another one. Okay, so new car depreciates 14.5% annually. A certain car. So this says annually here. Okay, so a new car, new $25,000 car. I can fix this. Come on. Can you still read that? Is it big enough? In the back? That's better. Okay. So a new $25,000 car appreciates, I guess I changed this to 14.5%. So I want you got some work to do here. Find the 1-year decay factor in percent change. Write V of x, the value of the car after x years. Find the 5-unit decay percent change. And write W of n, where n is the number of 5-unit periods. And find the value of the car after 13 years in, let's say, 2 different ways. Or let's say, no, actually 3 different ways. Okay, go. We'll walk around. Practice. Here we go. So we gotta get number one right, or else we're dead in the water. So if you want us to check your number one before moving on, that'd be a good idea. Okay, you gotta have number one. If you get number one wrong, everything else will be wrong. So check your number one with us.
What is the percent changes on the negative?
That's right. What's the percent change? It's not the percent change. Remember what the decay factor is. That's not the percent change. Okay, so with decay factors, you gotta remember, what is the percent change relative to your decay factor? What's the decay factor? Philosophy, I think most of us got that. What is the decay factor? 0.855. What does that number mean? Is that how much the car goes down? How much value is? Remains, right? That's how much you keep. Decay factors are the portion that's kept, or that remains. All right, so from that, what's the percent change? No, but this is, that doesn't count because this is the value. This would be the value of the car. You gotta use decay factors. You can't just stack together. Right, because this doesn't have nothing to do with starting for 10 years. 3 years later, this is starting from year 0. You guys good? Okay. So for 4, to help us obvious, you're defining a function w of n such that n is the number of 5-unit periods. That's the point. Okay, Alex back there. Did you get v of x? Number 2? This is what he said. Agree with number 2? Okay, how about Matt right here? This is Matt, right?
Yeah.
Number 3, how'd you get the 5-unit decay factor?
Power of 5.
Okay, so for number 3, he took 0.855 to the power of 5. What do we think? Yeah, because you imagine every year going by, you're going to multiply by that. And so after 5 years, how many times will you have multiplied by that? 5 times. And let's see what we get for that. What'd you get for that? Did you get a number, Matt?
Yeah, 11,422.
Oh, for just the decay factor?
Or, no, I got 0.4569.
0.4569, 0.457, that'd be a good if you're going to approximate. So this 0.855 to the 5th, I get 0.4569 or 0.457. All right, so then what is the corresponding percent change? Walden. Okay, how'd you get that?
By basically subtracting the 5-year decay factor.
Uh-huh. Yeah, so it's the same way we would do it if it was a 1-unit decay factor. We're just looking at this particular decay factor and we're getting the associated percent change. So we know that's how much you keep every 5 years. The vehicle is retaining about 45 or 46% of its worth every 5 years. That's what's kept. So what do we want? 100 minus 45.69. So the percent change, is it 54.31? Negative. So the 5-unit decay was 0.4569, and that makes a percent change of negative 54.31%. Okay, and who wrote the function Wn? Jose, did you get it? Tell me.
W of n equals 25,000 times 0.457 to the n.
This is what he's saying. Right, so it's giving us 2 different ways to model the value of the car. We got Vx, which models it year by year. Wn models it in 5-year chunks, right? 5-year chunks, where n is the number of 5 years. Okay, so now this number 5 is kind of being creative and really understanding these decay factors. Let's just come up with as many as you came up with. So how could you use these decay factors to get the value of the car after 13 years? So, okay, so obviously, if we could use the function v, and it would be v what? V of 13, right? So that would let's get that one out of the way. But my interest in this question is to see if you really can work with growth factors. Henry.
You can use W of n and then change n to 2.6.
Okay, so yeah, you change n to what?
2.6.
2.6. Okay. All right, now we got those out of the way. So let's do it using growth factors or decay factors. Jad.
You can put 25,000 multiplied by 0.457 power 2.
This is what I'm talking about. Okay, then
And then you multiply that by 0.855 power.
did you see that? So this is if this is someone who gets what's going on. He took the 5-year growth factor and multiplied it by 25,000 twice, and what did that give him? That's the value at 10 years. Multiplying that by the 25,000, the value at 10 years. But then he needs to go 3 years further. So he took the 1-year decay factor and multiplied by that 3 times. So another way, Eric.
How about 25,000 multiplied by 0.457 to the power of 13 divided by 5?
Okay, so that's getting a little, yeah, that works. Just we're getting to that later. You're overachiever. Good job. All right, anybody else? So is there another way we could do this? Yeah.
There's one more way. It's the same one as the one you have below, but you put 0.457 to the power of 1 and 0.855 to the power of 8.
All right, right. So you could do 1 5-year and then 8 1 years. And that would get it. That's good. What if I made it the 5-year to the 3rd? Could I get to it from there? Then what would I do after that? So I take 25,000 times 0.457 to the 3rd would give me the value when? 15 years. And then to get the value 13 years, I could divide by 0.855 2 times. That would take me back 2 years. So you can do that. You can do 0.457 to the 15th times 0.855, or divided by 0.855 squared. Okay, so web work and written work for Wednesday.
Thank you.